All right, so we've just proved Lagrange's theorem, which told us that for any subgroups of any group, the size of those subgroups have to divide the size of the group itself. Now we're going to do an application of this theorem. We're going to do an application in figuring out the Cayley table for a group of size 5, let's say. So all we're going to know about this group, G, is that it has size 5. And we're going to use everything we know so far, the Sudoku principle, as well as Lagrange's theorem, to try to see how far we can go in specifying the Cayley table for this group. Now, before we actually dive into that, I'm going to do one quick other diversion, which is going to be really useful, which is to introduce a concept, which is the concept of elements generating sets. So the set generated by an element of a group. So what is this concept? Well, imagine we have some group G, and we have some element of this group called little g. And now we're going to write this symbol to mean the set generated by G, by little g. And what this is it's just going to be the set you get by taking the identity operator, the identity element, taking G itself, and then applying the operation as many times as you possibly can. So G, apply the operation to itself, you get G squared. Apply G squared to G, multiply G squared and G, you'll get G cubed. And you just will kind of keep going. Erase this for a moment. And you'll do this forever. Now, if G is a finite group, which is all we're going to be working with for the moment, if G is a finite group, then we know that this eventually will end, right? Because since G is a group, it's closed, which means every time you're multiplying G by itself or G by some power of itself, you're always still staying within the group G. So at some point, you'll have run out of all the possible members of G. And, at that point, you'll have to loop back. So that means that there's some kind of largest member, which we'll call m minus 1, let's say. Let's call it n minus 1. We're choosing n minus 1 because then that makes the size of G equal to n. Okay? And we could say something a little further, beyond just saying that this set has to be finite. We can actually say that when we reach the end here and we multiply G, another G here, we actually loop back to E. Right? So in other words, we can say we won't have it's not going to be the case that we'll have E, G, G squared, and then it will loop back to G and just go through this cycle forever. Right? That's not going to happen. We're always going to, when we reach the end, we're going to loop back all the way to E. Why is that? Well, let's suppose that when we got to G to the n, this was actually equal to, let's say, G squared, for example. Well, then we can just multiply by inverses. We can multiply by G inverse 2 times. That'll result in G to the n minus 2. 2 of these G's will cancel, is equal to our identity. Which would mean that we had actually started looping back 2 elements before. Right? So we would have gone up to G to the n minus 2, we've got an E, G to the n minus 1 would be G, and then G to the n would be G squared. So, if this is the case, then this is not really the point where things repeat. You already have repeats. So, essentially what this means is that there's going to be some element n at which point our set loops back on itself. Now, the other important thing we can say about G is that this thing is not just a set. It is in fact a group, which we can write as, since every element of this set is in G, G must be, the set generated by G must actually be a group, and it is a subgroup of our group, big G. Now, why do we know that? Well, first of all, it's closed, right? If we take any G to the K and times G to the L, well, we just get G to the K plus L. Right? Multiply G by itself K times, then multiply it by itself L times, and multiply those two together, you get the same thing as multiplying G by itself K plus L times. K plus L, it's going to be another one of these guys. If K plus L happens to be greater than N, then we just loop it back around, and this becomes K plus L minus N. Right? And so we're always going to stay in this set, basically the powers of G. So it's closed. It's associative. Now, why is it associative? It's associative because multiplying 2 of these elements together say g to the k times g to the l again, ends up just being written as g to the k plus l. And if we multiply 3 of the elements together, so let's say we have m over here, this will just be adding another element up here. And clearly, it doesn't matter where our parentheses are here, because it doesn't matter where our parentheses are here. So we get associativity in this set. We actually inherited from the associativity of ordinary addition of integers. So that's kind of interesting. So we get associativity. Do we have an identity? Of course we have an identity. It's the same identity as we had in G. And do we have inverses? Well, yes. The inverse of any G to the K, this, G to the K inverse is just G to the N minus K. Why? Well, because G to the K times G to the N minus K is G to the N, which is the identity. Okay, so basically we're saying that if you take any group, take any of its members, look at the set generated by that element, we get a new subgroup of G. So this is a way to find subgroups of a given group. And we also have that the size of that group, of that subgroup, is going to be the lowest n for which G to the n equals E. All right, so this is a useful thing to keep in mind. And now we're going to apply Lagrange's theorem. So let's look back at what we were going to do. We had the size of G equaled 5. So we have somebody, your friend comes up to you and tells you that they have a group in their back pocket which has size 5, and you'll get some nice prize if you can guess exactly what group that is. So you want to go as far as possible in specifying the Cayley table. Your friend's satisfied with having the same group up isomorphism. So let's take a step back and for a moment forget that we know that Lagrange's theorem is true, and forget that we know this. Let's imagine all we had was the Sudoku principle. So, we have our Cayley table. We know we have an identity since the groups. We have E, and we have 4 other elements, A, B, C, and D. And the first thing we can always do is fill in these ones, E, A, B, C, D, E, A, B, C, D. But we can't really, what more can we do here using the Sudoku principle? Well, if we look at one of these guys, we know it can't be A, but that doesn't help because we still have 4 other elements it could be. If we look at one of these guys, it can't be A or B, but it still could be E, or it could be one of these other ones. And so, if all we knew was the Sudoku principle, we'd feel a little stuck here. And we could kind of go through and start saying, let's imagine that this one's E. Then what do we know? And then maybe that tells us, but even this is not going to uniquely specify anything because, for example, this guy could be C or D. And, so we could just write out a whole bunch of possible tables that would all look like logical possibilities to us, and we would hand one of those to our friends, and we'd have a pretty bad chance of getting the prize. So that's before we had Lagrange's theorem. But now let's apply Lagrange's theorem. According to Lagrange's theorem, any subgroups of G must have size either 1 or 5, right? Because they have to have a size that divides 5. 5 is a prime number. So I'll just say subgroup sizes must be 1 or 5. All right, we can't have subgroups of size 2, can't have subgroups of size 3, can't have subgroups of size 4. Now, let's see what that means for us. Well, what could A squared be? Well, the Sudoku principle allows us for this to be E, right? This could be E, or it could be something new. It could be one of these other 3. But it can't be E if we're using Lagrange's principle. Lagrange's theorem. Why? Because let's suppose this guy is E. If that's E, then if we just look at this little kind of subtable here, we notice that this itself is a group. It's closed, you have identities, you have inverses, and it's associative. This is actually exactly isomorphic to the integers mod 2. So that tells us is that if this guy was E, then we'd have a subgroup of size 2. But by Lagrange's theorem, we know that we can't have a subgroup of size 2, which means this guy can't be E. So we've already kind of started to get a little bit of mileage out of our theorem there. So this can't be E, can't be A. So It's either B, C, or D. Now, we're going to take advantage of the fact that we can really write this Cayley table in whatever order we want. So what we're going to do is we're just going to say A times A is something. And whatever it is, we're going to write it as the next column. Right? So we could imagine we hadn't yet written down B, C, and D. And we're just going to write down new elements as we go. So as soon as we realize we need a new element, we'll write it down as a new column. So A times A, we figured out it couldn't be A, it couldn't be E, so it's something new. Let's call it B, and now B has to have its own column. Right? And now we can fill in E times B is B, and B times E is B. And this is just taking advantage of the fact that we can write the Cayley table columns and rows in any order that we like. So what's next? Well, let's look at this guy, A times B. And actually, let's write down our result that we have already, which is, I'll write it over here, A squared equals B. And now we want to ask, what is A times B? Well, A times B, well, we already have that that A squared equals B, so we can plug in for B A squared, which will give us A times A squared, or in other words, A cubed. Now, A cubed, well, the possible choices we have at this point for this guy is that either it's not A or B, so either it's E or it's something new that we haven't seen yet. Could it be E? Well, if AB is E, then that would mean A cubed equals E. But if A cubed was E, then that would mean that the group generated by A would have size 3, right? The set generated by G would loop back on itself after A cubed, and A cubed would loop back, so we'd have size 3. And since it's a subgroup, we'd have a subgroup of size 3. But we can't have a subgroup of size 3, which means this guy cannot be E. So it's not E, it's not A or B, so it's something new. Let's just call it C. And now C, we'll give a new column to because it's something new. We can right away fill in these guys. Another thing we can notice is that the exact same reasoning applies for B times A. B times A is just A squared times A, which is A cubed, which again, A cubed has to be the same thing. You know, A cubed here, this is A cubed, this is also A cubed. So we can write this here. And we can actually say we found that A cubed equals C, right? Now, let's look at this guy. What is this? Well, it's not B and it's not C. It could be A, it could be E, and it could be D. Well, could it really? So we have 3 possibilities, E, A, D, according to the Sudoku principle, but first of all, B squared can't be E. Why? Well, if B squared was E, then we'd have this, our Cayley table would look like, our Cayley table for just E and B would look like this, which would mean that we actually have a subgroup of size 2, the inverse of mod 2, just like the same line of reasoning that led us to conclude that A squared couldn't be E. So this guy can't be E because then we have a subgroup of size 2, so let's cross out that guy. Now could B squared be A? Well, if B squared is A, well, we already have that A squared is B. So let's plug in, it's kind of, if we plug in for B A squared here, we'll get A squared equals A, which means A to the 4th equals A. And now we can multiply by A inverse, which will tell us that A cubed equals A times A inverse, which is just E. So if B squared was A, that would imply that A cubed was E, which would mean we'd have a subgroup of size 3, which we can't have. So it can't be A either. It has to be something new. There's actually now just one more thing that is new, which is D, because now we've run out of elements. So we can no longer do this move of saying, and maybe it's something new. Okay, so we have D here and here. B squared is D, but B squared is A to the 4th, so we can write this as A to the 4th equals D. Okay. Now, what about A times C? Well, A times C, C is A cubed. So A times C is A times A cubed, which is A to the 4th, which we already know is D. Same line of reasoning tells us that C times A is A cubed times A, which is A to the 4th, which has to be D. Those ones we get for free. But now what about these new ones? Let's look at A times D. Well, actually, this one's really easy. This one we just get for the Sudoku principle. Can't be A, can't be B, can't be C, can't be D, which means it has to be E. Right? So A times D is E. Now what about D times A? Well, we can do the same thing there. This has to be E as well. What about B times C? Well, B times C is the same thing as A squared times A cubed, which is A to the fifth. Now, A to the fifth has to be E, right? Because every element generates a subgroup. We know it's not a subgroup of size 1 because A is not the identity. The identity is the only thing which will generate a subgroup of size 1. So the only other possibility is that it is G, which has size 5, in which case A to the fifth equals E. So B times C is E. For the same reason, C times B is just A cubed times A squared, which is A to the fifth. So this is also E. Right? Now, if we look at B times D, you can kind of see that things are getting easier here. B times D is A squared times A fourth, which is just A to the sixth. But A to the sixth is just A times A to the fifth. And we already know that A to the fifth is E. So that means that this guy is just A. Right? Same thing for D times A. D times A is A to the fourth times A. Oh, I'm sorry, D times B. So D times B is A to the fourth times A squared, which is A to the sixth, which is again A times A to the fifth, which is just A times E. So this one is A here as well. C squared, C is A cubed. Exact same reasoning. A cubed squared is A to the sixth, so this guy has to be A. And you can also start to see the pattern, E, A, B, C, D, E, A. You might guess what these ones are, but let's just go ahead and finish it out. C times D is this guy. So C times D, well, it's A cubed times A to the fourth, which is A to the seventh. A to the seventh is A to the fifth times A squared. A to the fifth is E, so this is just A squared. A squared is B. So this is kind of actually working by just converting everything into A's first, and then converting it back into these. And by the same reasoning, C times D is B, D times C is just A to the fourth times A cubed. Everything follows the exact same way. This has to be B. And finally, D times D, D squared. D is A to the fourth, so this is A to the eighth, which is A to the fifth times A cubed, which is just A cubed, and A cubed is C. And there we go. So now you can tell your friend, you can hand them this table. It's a very symmetric, nice table as well, and you can get your reward. And it's worth kind of reflecting on how kind of powerful that Lagrange's theorem is, because we started off with just the Sudoku principle a little bit clueless. Like there were so many options, we had really no idea which one was going to be the right group. But it turns out that hidden inside those group axioms, actually we had packaged up enough constraints to fully specify exactly one group of size 5. And that's really what we found here, is that there's exactly one group of size 5 up to isomorphism. Every group of size 5 is exactly isomorphic to this guy. And it might look different at first glance if we imagine switching these around and changing to additive notation, but it is actually the same group. And in fact, this is exactly the group of integers mod 5. If we were to switch this to additive notation, we made this 0, 1, 2, 3, 4. You can check for yourself. The whole table would work out. For example, we'd have 3 plus 2 equals 0, which is right at integers mod 5. One last note on this is that, in fact, we really heavily lean on the fact that we had a prime number order here. And in fact, for any group of prime order,
we would have been able to uniquely specify the whole Cayley table, which means that there's exactly one group of there's exactly one group of prime size. And that group is always isomorphic to the integers mod prime, whatever the prime number is. So yeah, this is a little demonstration of the power of Lagrange's theorem.